Welcome learners. So today is the last lecture of this lecture series on engineering electromagnetics. We are on the last chapter, that is chapter number 7, talking about steady magnetic fields, and the lecture series will conclude when we are going to look into the final topics, that is on Stokes theorem and what is magnetic flux density and magnetic flux, and then we are going to solve some problems to better understand these topics. So what is Stokes theorem? So this theorem basically shows the relationship between linear and integral or linear or surface integrals. So it is similar to what we did with the divergence theorem, if you remember, in the third chapter, where divergence theorem basically showed us the relationship between different volumetric surfaces. So going back, divergence theorem was if we have a closed surface and the electric flux density was to be found as such. Again, this represents the total charge enclosed. So this charge can be found either using this set of the equation, which is a double integral, or we can also relate it to a triple integral in terms of volumetric division of a divergence around volumetric area. So basically the divergence theorem gave us two possible scenarios to find the total charge Q, either using the surface integral or the volumetric integral. In the same way, Stokes theorem gave us the same interpretation to find the current. So over here, this expression represents the Stokes theorem, and you can see it is giving us the options to find the unknown current by taking the line integral or taking the double or surface integral. You can see that the left hand side equation or basically represents the Ampere's law, where I equals to closed magnetic field in a line integral, and the right hand side equation is basically curl of that magnetic field rotating in any closed or small or differential surface ds. So the Stokes theorem basically gives us the possibility to find the total current either using the left hand side or right hand side of the equation. Now let us better understand how Stokes reached to this equation. So in order to do this, we first look into its definition. And the definition states that the line integral of a vector h around any closed path, so it is talking about this left hand side of the equation, is equal to the integral of the curl over any open surface enclosed by that path. So the remaining portion is talking about the curl of this magnetic field. So this mathematical expression is basically defined in terms of statements, and this is known as the Stokes theorem. So let us further understand the Stokes theorem. Suppose we have been given this surface S, and this surface is distributed into small incremental surfaces known as delta S. So this is one delta S, this is second delta S, this is again delta S, the edges are also delta S. So this whole bigger sheet of S is divided into smaller differential surfaces represented as delta S. Now, if we start with the right hand side of the Stokes theorem, where we can see that it is representing a curl, and we know that curl is represented as such, or one way to represent the curl is when it is equal to the current density J, and which was also our second Maxwell's equation. And curl is also represented as the Ampere's law in a closed loop divided by the surface it is present. So these are the two variations or equations to represent curl. So we start with the right hand side of the Stokes theorem, and we focus ourselves on these incremental or differential surfaces delta S. So if we look at one of the delta S based on the equation, we can see that we select delta S of this portion, and we can see that the magnetic field is rotating or technically moving in a curl in a counterclockwise or anti-clockwise direction, and the field or the current that is going to be generated is always going to be normal to the surface because this is a surface sheet. So normally we say that curl of H is having a subscript n, where n represents the normal to the surface. So this is one of delta S that we have selected. Similarly, if we select the adjacent incremental surface, let us select this portion, and we say that the magnetic field is moving in the counterclockwise direction. Same for the other one, and then we select the bottom region and adjacent cell as well, and the magnetic field is in the counterclockwise direction for all the fields. Now once we do this kind of rotation of the magnetic field with the arrowheads pointing where the magnetic field is moving and AN is normal to the surface, we can see that the right hand side of the equation is defined by this visualization of the magnetic field moving in a curled portion in a small region represented as delta S. Now what's the problem with this? So there is no problem. You can find the total current using the right hand side of the Stokes theorem, but sometimes you can face complications when solving the double integral. So remember, this is a surface integral, which means it's a double integral. Another problem may arise other than the complication is that most of the rotations might not form a complete curl motion, or most of the rotations or some part of the rotation among the adjacent cell. So let's say if this is cell number 1, its adjacent cell is 2, then its adjacent cell is 3, and the final is 4. They might cancel each other out. What is meaning of cancellation? So look at the first cell 1. We can see that the magnetic field is moving in the anti-clockwise direction. If we come to the second cell, we see that again the magnetic field is moving in the anti-clockwise direction, but at this point these two motions cancel the effect of each other. Same goes for the lower cells of 4 and 3, and then the adjacent cells as well. So these cancellations may create a problem in having an incomplete rotation or curl motion. And secondly, mathematical analysis may also be different or difficult to solve if we say that one cell is in one coordinate system and the other can be in another coordinate system. So hence this right hand side of the equation, although valid to find the total current, may be cumbersome because the currents or magnetic fields cancel each other out as shown over here. So in order to resolve this problem or to make it more easy, Stokes suggested that let us go back to the main surface and look at the incremental elements at the edges of this surface, or we can say at the border. So if we come to the border and apply the rotation of curl, so let us say this is the anti-clockwise or counterclockwise rotation. Same goes for the other elements at the border or edge of this sheet, and we can see that although the adjacent cells might cancel the effect of each other, so it may be something like this and it may be something like this, and this could be like this, but if we look at the outer edges, the magnetic field flows in the anti-clockwise direction from the first point and coming back to the beginning point. So if this is point A, this is point B, this is point C, this is point D, we can see that the outer edge, if we start from point A, goes to point B, then to C, then from C to D, and then back to A. So this means that a loop is created from A to B to C and back to A, and this loop is having the same magnetic field in the counterclockwise direction, and it is following a line. So the total amount of current can also be found if we take the line integral of the closed magnetic field in smaller differential lengths, which defines the Stokes theorem. So to summarize, Stokes theorem basically gave us an possibility to find the total amount of current either if we take the line integral, which is the outer boundary of this sheet, or we can take the curl of the internal incremental surfaces. So both ways we can use to find the total current, where the left hand side is more easy to calculate compared to the right hand side. So this is what the Stokes theorem is all about. Now let us look at the proof of the Stokes theorem. So let us say we apply the curl to any of the incremental surface, which is delta S. Again, the incremental surfaces are these divisions, these boxes as shown over here. So if we apply the curl to these incremental surface, so we know curl is defined as, so curl against subscript normal is defined as the Ampere's law or a closed form of magnetic field or a closed line integral divided by the surface it is being analyzed, then we can say that this normal can be represented by a vector or unit vector normal A of n. Then you just move delta S to the other side, so you're left with the part of the Ampere's law, the curl multiplied with the normal vector and S, and this in all combines to be surface or differential surface element. Hence we get the proof of the Stokes theorem. So this is a very simple straightforward proof where we utilize the equation of curl shown over here to reach towards the final equation of the Stokes theorem. Now let us look at an example, or rather a drill exercise, and see how we can find the Stokes theorem. So in this problem we have been asked to evaluate both sides of the Stokes theorem, and for the magnetic field given as H and the rectangular path with the regions of x and y and z, and the direction of the surface ds is normal always along the A of z. So let us solve this problem. We need to basically evaluate both sides of the Stokes theorem. So the Stokes theorem is, you have line integral of magnetic field enclosed equals to the surface integral of the curl of that magnetic field around any incremental surface, which is ds. So this is what we want to prove. This is equation number A. So we start first with the left hand side of the equation, and then we'll prove the right hand side of the equation, and their result should be the same. So in order to begin the analysis on the left hand side, let us first visualize this given magnetic field and see where the current can be as per the coordinate systems given in the rectangular coordinate system as x, y and z. So in order to plot this, let us use this representation. This is the rectangular coordinate systems x, y and z, and we have been given the ranges. So x is from 2 to 5. Let's say this is 0.2, sorry, this will be 5 because we are moving in the positive side, and this is 0.2 for the x-axis. So I can draw the x-axis which is parallel to y, and then y is given a value of +1 to -1. So let me extend it to -y. So let us say this is +1 and this is -1. So if I draw this, it will be parallel to x-axis. So I can see that my magnetic field is not found because z is equal to 0, so we will not use the z-axis. So this portion over here is the rotational magnetic field as per the coordinate given in the x and y plane. So let me give it a certain point. So we start from A to B to C to D and back to A. So this is basically my magnetic field, and I can say that my current, so where is the direction of current? So if I look at the magnetic field, it is around AX and AY. There is nothing on the Z, so magnetic field is around AX and AY. So I can say that my current is obviously, according to right hand rule, if I curl my fingers, the current is moving in the AZ direction. So the current is moving, let's say, over here. So this is A of Z. And how I know this is A of Z? Because D of S is to be at A of Z. So the current is moving in the upward direction. The thumb represents the flow of current. Magnetic field moves in the counterclockwise direction. So I can designate the arrows as such. So this is now my magnetic field, and this is the current which is moving in the upward direction along the z-axis. So this is the visual representation of my question, and this is the extended x field. So now once we have this, let us start with the left hand side, which means I have to evaluate the complete line integral of h dot d of l, which means I have to integrate from A to B, then I have to integrate from B to C, then from C to D, and again from D to A, so that my complete closed path loop is achieved. And this will be for all h dot dl. So I'm just writing it over here. So we begin first with A to B. So the first path is along A to B, and I need to find h dot dl. So this is from A to B, h dot d of l. Now what is h? So the value of h is represented obviously in terms of its scalar and vector components, h of x along a of x plus h of y along a of y plus h of z along a of z with the dot product of, now what is d of l? D of l is basically in the rectangular coordinate systems as dx along a of x plus dy along a of y plus dz along a of z. So this is the values that I have. Now if I look the path from A to B, I can see I am moving only in the x-axis. So this means automatically that dy and dz will be 0. And I'll only be left with the dot product of dx with a of x. So once I do the dot product, I know immediately that the y component and z component with the dot product will be 0. So I'll only be left with h of x along a of x dot d of x with a of x, and this dot product equals to 1. So in the question I'll be left only with 6xy a of x. So I'll be left with the value of h is over here. So it is just 6 of x and this is y, and I'll only be left with d of x, and then I can integrate from the limits. The limits from will be from 5 from 2 to 5 because x is from this range. So it is going to be from 2 to 5. Once we do the integration, so this is now with respect to x, so it will going to be 6y and x will be x square by 2 and the range will be from 0 to 5. If we incorporate everything over here, it comes out to be 63y. Now what is the value of y? Since a to b is along negative y, so it is going to be negative 63. So this is the answer for the first path, which is from A to B. Now let us take the second path from B to C and see, it means that I have to integrate from B to C what? H dot D of L, or the dot product. Now again let us use the same condition which we saw over here. Now in this scenario, my B to C is following the path of plus y. I can see it is going in the y direction. So it means that automatically x component will be cancelled out. So let me write it over here. H of x, a of x plus h of y, a of y plus s of z, a of z dot product with dl's only y component will exist. So I can say dy along a of y. Rest will be 0. This and this will cancel out. So in my question, I'll always only be left with minus 3y square. So it will be minus 3y square with d of y, and the integration limit for the y will be from minus 1 to plus 1. So once we integrate everything, we get the value of minus 2, because y square will be y cube by 3, and you input the limits, the answer will be minus 2. So this is the solution to the second path. Now we go from C to D. When we move from C to D, we are going in the negative x direction. So now we go from the path from C to D. So for C to D, we can immediately, without solving, we can do one thing. We know that going from C to D is in the opposite direction from A to B. This means whatever the answer we got for A to B, we can just write it for C to D because it is in the opposite direction. So I can write over here that C to D's direction is opposite to A to B. And for A to B, we got the answer of minus 63. Now when we write the answer for C to D, it's going to be minus 63y when the value is y is at 1. Why the value of y is at 1? Because here y is having a plus 1 value when we move in the upper direction from C to D. But if we put y value minus 1 or plus 1, it still remains at minus 63. So this is the solution to the third path from C to D. Similarly for D to A, again it is opposite. So if I write for the final path D to A, we know it is opposite to the path of B to C. We can again look, if I move from C to D, it is opposite to B to C, and B to C had the answer of minus 2. So I can immediately say that the opposite path, if the answer for B to C was -2, for this path the answer will be opposite, it is going to be +2. So we don't want to go into solving the integral of h dot dl, we can immediately write the path's value. Now once we have all the values, the left hand side can be written as the line integral or closed line integral of h dot dl is equal to, we sum all the values, so it is -63, -2, -63 and +2. So it is -63 -2 -63 +2, this and this will cancel out and I'll get the answer of -126 amperes. So this is the solution, or this is the current we found only using the left hand side of the Stokes theorem. Now let us use the right hand side of the Stokes theorem to get the answer, where the right hand side of the Stokes theorem is, we basically do the double integral and take the curl of this value of h, and then we find or take the dot product with the surface or differential surface. So for the right hand side, I'll write the portion we want to take the curl of h and dot product with the surface element. So this is what we want to figure out. So this means that first I want to know what is d of s. So d of s is going to be, so what is d of s? Normally d of s is normal to whatever where the magnetic field is moving. So we take the normal component over here. We know if we go back to image or the axis, we know that our components for the rectangular coordinates for d of s comes out to be d of x, d of y, d of z. Since the current is in the z direction, so we can immediately say that ds is going to be just the component where the magnetic field is existing, that is dy dz along the normal vector which is a of z. So this is basically our differential surface element for the rectangular coordinate systems. Let us say d of s along z. Now once we have this, we just want to figure out the curl. So we have figured out the value of d of s, and now let us find the curl. So curl of h is basically in the rectangular coordinate systems as the determinant of a of x, a of y, a of z, partial by partial derivative of x, partial by partial derivative of y, partial by partial derivative of z. And let us look at the question. On the question, what is the value of h? It is existing for ax and ay, and the z component is equal to 0. So we can write it is going to be 6xy minus 3y square and z is equal to 0. So we can then take the determinant of this. So first for the ax unit vector, we block these elements or we make a t, and we can see it is immediately going to be 0 plus 3x square. So this comes out to be 0, and we can see that partial derivative is with respect to z, and there is no z component over here when we are multiplying this, so it is automatically 0. Then we take the second value, let us say a of y, so it comes out to be, so we take this component now along with the upper one, so it is 0, and again with respect to z we have nothing over here, so it will be 0. And then for a of z we take these components over here for the determinant. So with respect to x and y we are going to have these combinations, so the value comes out to be, you take the partial derivative of x with y, so this is 0, and you will be left with y as 6x. So this is the solution we get for the second value, or let's put it at 0 minus 6x. So the answer then comes out to be 0 0, and you get minus 6x along a of z. So this is the curl's answer. Now we have the curl answer, we have d of s, just incorporate everything into the equation. So the equation on the right hand side is that we are going to take the surface integral. So don't forget the surface integral. This is closed surface integral of curl of magnetic field dot d of s turns out to be, so we take the integral minus 6 of x along az with what is d of s, it is d of x, d of y with az, so this and this equals to 1, and the limits will be for x and y. So value of x is from 2 to 5 and y is from -1 to +1. So we then solve this integral, and it's a quite easy integral. You take the sixth value out and we can solve it for x and y. So first with x, it is going to be x squared by 2 for the limits of 2 to 5, and for y it is going to be y with the limits of +1 to -1. Once we solve this, we get the value of so this is 2, this is 3, so it is going to be -3, and x will be 5 square is 25 minus 2 square is 4, so it is going to be 21 for x, and for y it is going to be 1 plus 1, it is going to be 2, so it comes out to be minus 126 amps. And this is the same answer which we got over here for the left hand side. Hence we can say that the left hand side is equal to the right hand side, and both the sides of the Stokes theorem is proved. So this is the solution to the problem relating to the evaluation of both the sides of the Stokes theorem. Let us look at another example and see what other challenges we can face when solving the Stokes theorem. So in this question, we need to find, okay, so this question is basically related to the figure 7.7. I'll draw the figure for you, and again we have to solve the Stokes theorems both sides. So let us take one of the side and the rest you can take as an home exercise. So the surface that we want to draw is specified by radial component at 4, theta is from 0 to 0.1 pi and phi is from 0 to 0.3 pi. So this means this is a spherical coordinate system with r, theta and phi, and we basically, and the closed path is composed of 3 circular arcs. So the closed path is maybe forming a cone, but we'll look into this, and the H field is given in the components of r and phi. So this is part of it. There is no theta, so I can say that one of the component is missing. So we have been asked to again evaluate both sides of the Stokes theorem. Okay, so both sides of the Stokes theorem, again I'll write the solution for this. Again, Stokes theorem is line integral of h dot dl is equal to surface integral of curl of h with that differential surface. So this is what we want to do. Let us do the left hand side. Right hand side you can take as an home exercise because we have just solved the right hand side in the previous example. Okay, so what we have the value of magnetic field. Magnetic field is having the components along the radial, which is AR, and it is having the component along phi, which is A phi. So which means that H theta is 0. So this is not given from the equation or the question. Okay, and we can write the values to make it more simple. It is going to be 6r sine of phi along AR plus 18r sine theta cos of phi along A phi. So this is the value of the magnetic field intensity that we have, and let us see what we can do with this. Let us try to understand how we can visualize the 3 arcs that are in a closed path. So we draw the coordinate systems to better understand what the image is saying to us. Okay, so we normally have the value of z, r is a radial component, and theta and phi is given. So for theta and phi, we can say, okay, so normally z is something like this, so we normally extend outward from the z-axis. If this is the origin, so the z is currently not given, but we extend outward from z to get the radial components. And what about the phi? So the phi is always moving from x to y, so that is another thing that we can take. It is moving from x to y. Now phi is from 0 to 0.3. So okay, this is 0.3, the maximum value. So let us try to figure out what this will be. So if we start from 0 and go to pi, so this is the starting point and this is the maximum we can go. So this could be 0.3 pi. So this is for phi. in the xy plane. And when we talk about the theta component, we know that theta is starting from this point and it is going in the downward direction. So we can say that the value of theta is from 0 to 0.1 pi. So this is my theta, and it goes on the other side as well. So 0 to 0.1 pi. So this is for theta in the both side of the z-axis. Then the components that we are interested is the radial component. So if we extend from 0 and move in this side, this is one of the radial component. If we move from 0 to the other side, that is another radial component. And if we basically join it to the center and then we move the combination of phi from 0 to pi, this is the third radial component. So we can say that this is our first arc, this is our second arc, and this is our third arc, where the value of r is over here on the other side of z, and on this side when we follow the phi line. So we can say that this is basically making some kind of a cone, and we are just interested in the upper side of the cone. So this is what we are getting. Again, this is extended to phi and 0. So hope you remember this. We did this in chapter number 2. So let me highlight which is the region that we are interested. So this is the region 1 from the first arc, this is the second arc that is following the phi direction, and this is the third arc that is on the other side of the theta. So theta has two sides and phi is basically from xy plane, that is from 0 to this direction. So this is basically the representation that you might see in the book as well. Now let us solve this problem once we got the visualization of how to go about this. So keeping in mind that the radial value, so I'll select the pointer again, radial value is 4 and phi and theta are provided in the question. Okay, so we start with the left hand side. Again, for the left hand side, this is the value of h that we have. So for the left hand side, we basically have, you take the closed line integral for h dot dl. This means we find the closed path in the first circular arc, with the second circular arc, and with the third circular arc. So we find h dot dl for all the three scenarios. And now we start with the first circular arc. So let us say this is arc number 1, which is this region over here. This is the circular arc number 1. So for the circular arc, I'm going to change. Okay, let's stick with the red first. Okay, for the circular arc, we can see visually that the theta is varying from 0 to 0.1 pi. Radial component is 4, and here phi is 0 because phi is at this point. So if I extend this, phi is at 0. So this is the coordinates or the values of r, theta and phi. Now in order to find h dot dl, we already have h. What is dl? So dl for the spherical coordinate systems is given as dr into ar. Sorry, the rectangular, the cylindrical coordinate systems. The spherical coordinates, because we have r, theta and phi. So dr into ar plus r d theta along a of phi, and then we have d theta a phi with r sine theta. So this is the differential element for d of l in the spherical coordinate systems. So now what is h dot dl for this first circular arc? H dot dl, it is going to be, so the value of h is 6r sine of phi along ar minus 18, sorry, plus 18 r sine theta cos of phi along a phi, and you take the dot product with which component. So if we look at the first circular arc, we are only having the value that is changing, and the varying value is around r d theta and a phi. So we can say that the radial component is fixed, so it is 0. There is no rotation in the phi component because it is at 0. The only value that is varying is r d theta and phi, because theta is from 0 to 0.1. So this means that we'll just multiply it with r d theta along a of phi. So once we do this, we can see that the only component left will be the second part of the problem. But this is, let me check if I have written the value. No. So this is a of theta, as this is a of theta, not phi. Okay, because theta component is a. So once we do the dot product, we can immediately see that the answer will be 0, because a theta with a phi dot product is 0, and then a theta with a r dot product is equal to 0. So the first circular arc gives us the closed magnetic field having a value of 0. Now let us come to the second circular arc. So for the second circular arc, I'll use this. So now for the second arc, we are moving from 0 to 0.3 pi. So this is the region. So this is from 0 to 0.3 in the phi. So for the second circular arc, let me write arc 2. What are the components that we have? So in the second circular arc, now phi is from 0 to 0.3 pi. The radial component remains the same. And what about theta? So theta is at its maximum value of 0.1 pi. So theta is having a fixed value of 0.1 pi. So this is what we have. So again we find the closed loop for the second arc, which is h dot dl, and the value of h dot dl. So what is dl now in this case? Going back, so the value of dl in this case, since we have just so the radial component will be 0, the theta component will be 0, we'll just be left with the third part, which is the phi, because phi is varying. We can see phi is varying over here. So this means that let me write the value of h first. So the value of h is 6r sine phi. So it is 6r sine phi along a of r plus 18r sine theta cos phi along a of phi dot. Now what is the dl? So dl is just going to be this portion, the rest will be 0 because only phi is varying. So it comes out to be r sine theta d phi along a of phi. Now again, if we look at the dot product, so this component's dot product with this component will result into 0. Only will be left with the second term. So we will be left with 18r sine theta cos of phi with dot r sine theta d phi. So this is what we are left with. Now let us do the integration of this. So this means we will have the integration will be the limits of phi from 0 to pi. So let me put the integral. So this is h dot d of l. The integral will be from 0 to 0.3 pi, and again this is for phi, as you can see over here. So in terms of phi, I can bring the coefficient out, which will be 8r sine theta. So this is another r, this is another r. You can say r square sine square theta, and the integration will be from 0 to 0.3 pi of cos of phi d phi. Now this is a simple integral. Cos phi is going to be sine of the value inside. So if we continue with the integration and put in the values, so I can say 18. What is the value of r? It is 4. So I can just say 4 square. Then sine square. What is the value of theta? So if I go back, theta is 0.1 pi, but this is in radians, so I can convert it into degrees. So it is going to be 0.1 into 180 degree, and this is, sorry, a whole square. So this is basically whole square, and then cos is in the sine phi. So this is the integral with limits 0 to 0.3 pi. That's it. So once everything is there, you incorporate it and you solve it, you should get solution as 27.501 sine, what is phi, again from radian into degree, I get this value 0.3 into 180, and it comes out to be 22.248 amps. So this is basically the answer to the left hand side of the equation. For the second part, remember, Now let's come to the third part. So the third part is basically the third arc, we will say. So arc number 3. So arc number 3, so this is the arc number 3 that we want to know. So if you look at arc number 3, it is opposite to arc number 1. So whatever the answer we got for the first arc should be the same but with opposite sign. And we know that the first arc had the value of 0. So without going into the integration, we can say that since this is opposite to arc 1, the answer for h dot dl, left hand side of the Stokes theorem, is also going to be 0, and that's it. So if we say that the complete solution of the left hand side is going to be h dot dl in a closed path is going to be, you sum everything. So the first solution answers was 0 plus 22.248 plus 0, it comes out to be 22.248 amps. So this is the answer for the left hand side. Similarly, you can do the right hand side of the Stokes theorem. So the right hand side of the Stokes theorem is that you take the curl of the value of h given in the question over here. This part is also part of the question, and then you take the differential element. So this is something that we have recently seen in our previous example. So I leave the second part for you to solve. So the right hand side of the equation, I'll just change the color so it becomes, so the right hand side of the Stokes theorem, which is curl of h with ds, and don't forget it's a surface integral, is for you to practice at home, and the answer should be the same as this one, which is 22.248 amps. You can use the curl of h for the spherical coordinate systems as 1 by r sine theta, r square sine theta, and the value will be around ar, a theta, and a phi, where this is r a theta and this is r sine theta, then partial derivative of r by partial derivative of theta, then partial derivative of phi, so this is r, and then the value of h for this case comes out to be 6r sine phi. So it is going to be 6r sine phi. For the second part, this is going to be 18, so there is no theta, it is going to be 0, and phi is 18r sine theta, so this will be 0 and this will be 18r sine theta cos of phi. So you can use this equation to find the curl and then the surface integral, which is a double integral for the right hand side, and thus the question will be proved with the same answer. So this was the solution to this problem. Now let us come to the last topic of this lecture series, and this is about magnetic flux. So in the beginning of this chapter, we talked about few relationships that we agreed upon, and those relationships came from the proofs we did in the electrostatic section, where we said that the electric flux density is equal to electric field intensity. In the same lines, the magnetic flux density B will be equal to the magnetic field intensity, where all of these elements are vector quantities. Then we read that the electric flux is equal to the total charge enclosed. In the same way, we are going to now look into the magnetic flux that corresponds to the magnetic flux density B in a closed surface of ds. So this is magnetic flux density, which means it is basically telling us how much amount of magnetic field is existing in a closed surface, and it is going to be equal to the magnetic flux over that surface. So if we take any closed object and we say that that object has magnetic field or magnetic flux flowing through it, so it is going to be the same if we calculate the magnetic field lines in the form of magnetic flux density. So this is what the equation is saying. Again, some parameters associated, that whenever we are finding magnetic flux, it is represented in the units of Weber. B is the magnetic flux density, which you can use this equation to figure out in the units of Weber per meter square or Tesla, and ds is the differential surface element or a small surface that we have selected. One more thing associated over here that leads to the third Maxwell equation is that whenever we talked about divergence, we said that it depends upon the total volume charge for the electrostatic field. So if you remember, we had the Gauss's law. Gauss's law basically said that the total charge is basically equal to the enclosed surface electric flux density over that surface, and then we said that the point form of Gauss's law was something like this, where divergence of D is equal to rho V. Now for the magnetic flux, we can say that the integral equation is represented as such, but if we take its divergence, it will always be zero. Why is that? Because of something that is known as magnetic monopoles, and they do not exist. What does it mean? That, for example, if we talk about this portion of the equation, we say that, what does this mean? This means that we have any charge and the energy from that charge is basically leaving in the outward direction, and thus we define this energy leaving in the form of the divergence, and we said that divergence is also equal to the total amount of volume charges on this closed surface. But when we apply the same theory to magnetic poles, it is not valid, because if we take any magnetic, let's say a permanent magnet, we know it has a north pole and a south pole. So the energy always initiates and emerges from north and goes towards the south. But if we break this magnet into two halves, let's say if I break this magnet into north pole and a separate south pole, they cannot exist separately. The breakage will again by nature lead to the other elements bring up its own pole. So the missing south will be available on the first or left magnet, and the north pole is going to exist automatically in the second breakage of the magnet. This means that the no independent monopoles or sources exist, and thus whatever leaves the north pole will enter the south pole and vice versa, and thus there is no divergence, or the energy that is leaving is equal to the energy that has entered. So the divergence of magnetic field will always be equal to zero, and this is also known as the third Maxwell equation. So let us look at an example to how we can find the magnetic flux. So again, in this question we have been given a conductor that is lying along the x-axis carrying a current of 10 amperes. So this is x, y, z coordinates. The current is moving in the x direction. The piece of conductor is lying on the xy plane, and the strip has a surface area of d of s. So we have selected only one surface. The current is in the x-axis. This means, as per right hand rule, if the current is moving in the x-axis, the magnetic field is moving over the x-axis, or it is going towards the negative z-axis onto the strip, which is d of s over here. We have been asked to determine the magnetic flux, which means we need to find phi. So the symbol of phi is obviously a straight line, and for the region that is bounded by x having a value of 1 to 3 and y from 1 to 4 in the negative z direction. So we can say that the surface sheet's normal is towards the negative. So in order to find the magnetic flux, we can utilize this equation, which is the surface integral of magnetic flux density and then dot product of with differential surface element. So we start by the solution of saying that we know that for an infinite lawn conductor, the magnetic field is given by this equation, and in order to find the first unknown variable magnetic flux density, we know by the relationship B is equal to mu naught H, where we incorporate the value of H from above. So we get the value of mu naught I divided by 2 pi. Now what is rho? Rho is along the y-axis. Why? Because we are looking at the magnetic field B, and you can see from the image that magnetic field is moving towards the y-axis. So this is the rho, and the unit vector is normal in the AZ direction, which is going in the downward direction. So that's why we have a negative sign. So this is how we got the magnetic field. Again, the negative z direction is provided in the question itself. So first part of the equation for the magnetic flux is figured out. Now we go to the ds. So in order to find ds, we get the value of minus 2y minus 2 dy along a of z. So again, what does it mean? So this is the sheet that we have. We know that x is from 3. So let me see where is x is from 1 to 3. So this is 1 to 3. This is the rate of change of x, and y is over this distance, which is from 1 to 4. So this is from 1 to 4. So in order to find the differential surface, we know that differential surface is basically d of s along z is normal vector to the d of x and d of y. So in this scenario, we have just taken one component, which is along A of z, normal, negative A of z, and we have just focused on the differential element of x. So the why we have focused, because the current is in the x direction and magnetic field is along the y direction. So we are not finding the magnetic field, we are basically looking into the current, and then the difference of current is 3 minus 1, which comes out to be 2 along d of y. Hence we got this solution. Now once we know B and D of S, we can just use the surface integral to find the unknown magnetic flux, and here it is now a single integral, not a double integral. So this is dependent on y. So you incorporate the values of all the values that we have seen previously, so you get the answer at 5.5 microweber, and this is the magnetic flux that was required. Hopefully this solution is easy to comprehend, because these are the things that we have thoroughly discussed in the second chapter. To conclude this lecture series, let us look at another example related to the magnetic flux, so the things become quite clear. Let us say I have a radial magnetic field H as 2.39 into 10 raised to power 6 divided by rho as cos of phi along a rho. So this is given to me, amperes per meter, and we want to find the magnetic flux, which means we want to find magnetic flux occurring when the ranges of phi and z are as such. So phi is from 0 to pi by 4 and z is from 0 to 1 meter. So we have such a scenario. Let us see what we can do with this. So let us first understand this by visualizing that what kind of structure we are dealing with. Again, structures help us to solve the numericals without going into the integration, as we have seen with previous exercises. So this is in the phi and z, so it is a cylindrical coordinate systems, obviously, and what we have is we have z from 0 to 1. So let us say that something is coming out from z and it is going in the opposite other direction as well. So this is 0 to 1. The phi value is from 0, so let us say this is 0.045, and we know that it should go from 0 to 2 pi, but let's say if it reaches 0 to pi, this is 0 to pi. Where could be pi by 4? Let us say somewhere over here. So 1/4 of this is your phi, this is your 0 of the phi. So the structure is something like this. So we are taking this portion from 0 to pi, and this is for 0. So we can see that we are getting this kind of a image, where if I join the radial components as such, so I am getting this value. So this is basically the value where z equals to 1. And where is the value of the radial component? The radial component will always be in the direction, in the outward direction. So I can say that this portion is of interest to me. So the sheet on this cylinder is over here, where this could be my radial component A of rho. So this is some portion of a cone or a cylinder's portion, where we are just taking distance from 0 to pi by 4 as given in the question, and z is from 0 to 1. This is 0 and this is the direction of 1 for both the cases. Okay, once we have this, now what we need to do, we need to find the magnetic flux. So magnetic flux over here is simply the surface integral of magnetic flux density B of S and a dot product with the surface or differential surface element. So this is the equation that we want to prove or figure out. So we don't have B, but we can figure out B from H. So we can say that B is equal to mu naught H. We know that magnetic field and magnetic flux are related as such. So I can use this equation. So this is going to be mu naught, and this is a surface integral. Now we have H dot D of S. Now magnetic field intensity H is given to us, and we just need to solve this equation. Now what is D of S? So D of S is the surface integral, the differential surface element, and for the cylindrical system, we know that since the radial component is only existing and the motion is along phi, so I can take it as rho d phi d of z along a row. So this is the differential element, and we have talked about this a lot. So now since I have everything, just incorporate everything into the equation. So magnetic flux is equal to, replace the value of mu naught with the value 4 pi into 10 raised to power minus 7, and let's take the double integral. So the integral is going to be along phi and z, because rho is a radial component and it is given. So this is our phi and this is our z. So z is from 0 to 1 and phi is from 0 to pi by 4, and the value of h is 2.39 into 10 raised to power 6 divided by rho cos of phi along a row dot, what is d of s? You have rho d of phi d of z along a row. So this and this equals to 1. Rho and rho with cancel out, and then you just have to integrate with d of phi and d of z. So once we do this, we can say 4 pi into 10 raised to power minus 7. I'll bring the coefficient out, which is 2.39 into 10 raised to power 6, and then we'll do the integration with this. So if you go with z, so it is just dz. So the integral will be for z with dz, and then you have cos of phi with d of phi. So with these two, I can say I will be having z from 0 to 1, and cos of phi is sine of phi from 0 to pi by 4. And once you solve these elements, you will get the answer also. This will be 3.003, and inside we have limit is for z is 1, and this is 0.707. So finally the answer comes out to be 2.12 Webers. So this is the magnetic flux, which we figured out by using a very simple equation, that is the closed form of magnetic flux in a differential surface element. And this concludes our complete electromagnetic series, with the last chapter being from chapter number 7. Hope you enjoyed the lecture series and you learned something new by looking into the concepts, understanding them with numerical solutions.